Hello, and welcome to another wonderful episode of the New York City Category Theory Seminar. Today, we're going to have Arthur Parzygnat, a former CUNY student, may I interject, talk about a functorial characterization of classical and quantum entropies. This is our last talk of the fall semester, and we have a whole lineup for the spring coming up. Arthur, but you have to start by telling us something about yourself. Where did you do your undergraduate degree? We know you did your graduate degree in CUNY, and where did you go afterwards?
So I actually did my, thanks for the introduction, Nelson. I actually did my undergraduate at CUNY as well in Queens College. In fact, John Turilla was one of my professors, and Scott Wilson, if he's in the audience. And then I went to the Graduate Center where I did my PhD in technically physics under Parzygnat A. And I also had a math advisor who was Scott Wilson when I was there. Then afterwards, I went to UConn for 3 years as a postdoc, and now I'm here at IHES in France.
Okay, good. Take it away.
Okay, great. So I'll be talking today about functorial characterization of both classical and quantum entropies. And here's the rough outline of my talk. I'm going to try to make it basic, and I'll try to go slow. And I would actually prefer if you asked as many questions as possible, especially if there's something you misunderstood or it may prevent you from understanding what comes out of my mouth afterwards. So I'll review the Shannon information loss as a functor, which was something that was developed by Baez, Fritz, and Leinster back in 2011 or so. And then afterwards, I'll talk about quantum probability spaces and the von Neumann entropy. And I'll focus specifically in the finite dimensional setting. And then I'll introduce a von Neumann entropy type functor that also looks very similar to the Baez, Fritz, Leinster functor for the Shannon entropy. And then I'll describe some of its fallbacks, and we'll fix those fallbacks by looking at categorical structure that actually fixes two problems at the same time, that of convex fibrations and mutual orthogonality. And then I'll briefly describe the functorial characterization of von Neumann entropy. And if, I think the first minute is probably the most important minute of the talk, I think. So if you get anything out of this talk, it's that this is sort of a picture for what this entropy classification looks like. On the base here, I've drawn this black circle that sort of represents the category of finite dimensional C-star algebras and star homomorphisms between them. And over each algebra, like A or B, and by the way, if you don't know what a C-star algebra is, that's totally fine. Just think matrix algebra from linear algebra, and it'll be fantastic. So M by M matrices, or direct sums of them. And so sitting over each algebra, I have a space of what I call physical states. And sometimes they might look like a simplex. For instance, if the algebra is commutative. If the algebra is non-commutative, then it might have a more interesting geometrical structure. And each star homomorphism gives rise to a weight that transforms states from one space to another. Notice that the directionality goes backwards. And this picture forms what's called a fibration. And if you've heard of fibrations from topology or bundles in geometry, you should have this picture in mind. It's just that these things are replaced by categories instead. And on the right-hand side, you just have what looks like a very strange thing. There's a category with a single object on the bottom and morphisms that are real numbers. And so entropy is just a way to measure this change associated to a map of algebras and how states change under that specific process. So that's roughly the main idea. And I'll explain a lot of these ingredients throughout the talk. So let's start in the classical setting by first describing a specific category called finprob or fineprob. These are, the objects are finite sets, X, together with a probability measure on X. So this is just a collection of numbers between 0 and 1 who sum up to 1 when I add up all the elements of my set X. And if I have two such probability spaces, a probability preserving map is just a function from one space to the other that pushes forward that measure, that pushes forward the measure. And if the formulas seem uncomfortable, I'll draw a picture in a moment that'll, I think, make a lot of sense out of this. And this is at least how I like thinking about these maps, these morphisms. I learned this picture from Gromov, by the way. And what it's supposed to depict is that on the top, you have a probability space X, and each of these water droplets are actually represented by elements in the set. And the size of the water droplet dictates the probability or the mass or the volume, however you like to think about it. And if I add up all of these volumes, then I just normalize that to 1. So that's one way of thinking about what a probability space is in terms of water droplets with a given volume. And any function from that set to another set is gonna identify potentially some elements, right? Every function is allowed to send 2 elements to 1, but you can never send one element to a multiplicity of elements. That wouldn't define a function. So what I've depicted here is over each element in the codomain of F, you can look at all of the elements that landed into that element under the map F. So for instance, under this first element in Y, it came from 3 elements in X. And then the probability preserving condition just says that the sum of the volumes in the pre-image equals the volume of the element in the codomain. So this is how I think this picture's, I'll be honest, this picture actually helped me prove a lot of theorems. So I think it's a very powerful picture, actually. So this is what the objects and morphisms in the category FinProb look like. And the Shannon entropy is going to be a quantity that we associate to these objects in this category. So to each probability measure, we define it as this specific function, which we set to be 0 if px happens to be 0. And it has many interpretations. I won't really go into these, but I'll just mention a few very briefly. For instance, it can quantify the resources needed to store information and data compression. For instance, if you have a message, let's say in some alphabet, and you know the frequency at which certain letters happen to appear, there's a probability distribution associated to that frequency. And you can, instead of associating like arbitrary bits to those messages, you can associate clever choices of certain combinations of bits that make you reduce, that allow you to reduce how many bits you use based on the probability at which these specific letters occur. It can also be used to describe the degree of uncertainty in that probability measure. Like if you interpret the elements of X as things that could happen, like for instance, weather patterns, for example, if it's gonna rain, be sunny, or a foot of snow. And it could also be used as a measure of biodiversity. And though I have to admit, I haven't looked at this book yet, but Leinster recently came out with a book that I believe discusses this. So maybe some category theorists might be interested in checking that out. And there are many other interpretations as well. But what is actually going to concern us today is actually the difference of the Shannon entropies associated to a probability preserving map. And we're going to interpret this as the information loss associated to that specific process. And the picture of water droplets helps with this interpretation, because if we draw this picture again, we see that the map identifies certain water droplets. So things that had a distinguished element to themselves are now combined in their codomain, and those specific associated ratios to the probabilities or to the volumes that they had before they were identified, that information has been lost. And you can quantify this specifically by explicitly computing the associated entropies, and it always turns out that the entropy of the codomain is always less than the entropy of the domain. Therefore, the difference in particular is always non-negative when I take the difference of HP minus HQ. So HP here, P is the one on top. I think of that as my initial probability, and Q is the one on bottom. I think of that as the final probability after this process has occurred. And if I take any two of these processes, unfortunately, drawing a picture would be a little bit complicated. I have to draw a three-dimensional one, collapse one face, and then another one. And I didn't have enough time to do something fancy like that. But you could imagine such a thing happening. And if I write down the information loss associated to the composite of two such processes, and I take the entropy difference of the endpoints, then that's going to equal the sum of the entropy differences associated to each of the constituent processes. And so the information loss actually defines a functor from this category, where I just take this difference of these two entropies associated to the codomain and domain, and I always get a non-negative number. And this category here, BR, is the one that I showed at the very early part of this talk, it has a single object, and then the morphisms are all non-negative real numbers, and the composition is defined by addition in that category. If another way of thinking about this, if you've never seen this category before, you can do this with any monoid. If you have any monoid, which is a set with a binary operation satisfying some associativity law and things like that, you can always view a monoid as a category by just throwing in an arbitrary object in that category, and then all the morphisms from that object to itself are the elements of that monoid, and the composition is obtained from that binary operation. But this entropy difference actually satisfies even more properties than just being functorial, which was actually kind of an obvious property if you think about it. We're just taking this difference of two endpoints. But something that's maybe not as obvious is that if you take two such processes, you can imagine flipping a weighted coin, like a coin weighted by some probability lambda, where you decide which process you want to perform. And if I draw this in this way, what I get is a new probability space where I've taken the disjoint union of all of the elements in both of the spaces, but I've rescaled all of the volumes by the scale that I've chosen, by the scale lambda that I've chosen. So in this picture, I've taken lambda to be 1/4. So if you compare the blue picture on the left with the blue picture on the right, the sizes of these water droplets are about 1/4 the original size, and then the red ones are just 3/4 their original size. But the map F disjoint union G acts in exactly the same way. It just acts on F on the blue part and G on the red part. So it's just the disjoint union of functions. But it nevertheless, the probability preserving condition still holds for this modified probability distribution after I flip this coin. And you can compute and show that the resulting information loss equals the convex sum of the differences of these entropies. And this is not a usual property that ordinary entropy satisfies. Entropy is not an affine functional on probability spaces. And the reason is because you get an extra term coming from the entropy associated to that coin flip. But when you take the difference, that extra term cancels. And there is a natural convex structure on this category based on the previous slide, which we can formalize as follows. If you can define a functor on the Cartesian product of this category with itself that takes each pairs of objects to a new object. So it takes two probability spaces weighted. This is just formalizing what I had intuitively explained on the previous slide. And the probability measures exactly what I said. You localize P on the part X where we had it earlier. You rescale it by lambda, and the part Q, you localize it on Y, and then you rescale it by 1 minus lambda. And the way it acts on morphisms is just by taking the disjoint union of those two functions. And there's also a convex structure on BR. you can always take the usual convex combination of real numbers, and that also gives you a functor from BR cross BR to itself for every number lambda between 0 and 1. So we have these two convex structures on both FinProb and BR. And we can make sense of what a functor is. We can make sense of affinity of a particular functor. And that is formalized by saying, I have these two categories with these two convex structures, these functors that allow us to take convex combinations. I can apply a specific functor S on each of the parts, or I can apply S after I've taken the convex combination. So in our previous example, we were talking about the entropy difference. And a functor is affine if and only if this diagram commutes for all lambda. So again, the Shannon entropy is an example of such a functor. And you can ask, is that the only such functor? I mean, I guess you could think that there are many such functors that satisfy those properties, but it turns out that these properties actually uniquely characterize the entropy difference. So more precisely, if we have a continuous affine functor, and I haven't said what continuous means, but pretend that there is a notion of continuity that you can impose on such functors, then there exists a non-negative constant such that this functor, when applied to a specific process, gives you the entropy difference up to some constant C. And the constant C can be determined, for instance, by any reasonably nice morphism, like if you take an actual coin flip and then you forget and you don't look at the result of the coin flip, that's just looking away, then that you can just declare the entropy, you can declare the assignment that S gives to that and specify that non-negative number, and that will be your constant C. So the constant C is not really that relevant. The point is that you get the entropy difference.
Arthur, does continuous mean what we think it means for a functor? It preserves limits or something?
Okay, great. Because you could have asked a different question when you said we, but yes, let's take that simpler one, which is you can make sense of what it means to take sequences, for instance, in your category. If you take sequences of sets, you know that those things jump around a lot. So we would say that a sequence converges if and only if the sequence of morphisms converges if and only if the endpoints are fixed after some finite distance in your sequence. But then the map, F also eventually has to stabilize too. But the probabilities can change because the probabilities have like a continuous range of possibilities because they're defined on a simplex. So the function itself eventually stabilizes, but the probability measures can be perturbed continuously. But yeah, you would use the usual topology on a simplex to make sense of what it means for those sequences to converge. And then in the BR, we just use ordinary convergence of sequences in the real numbers. Thanks for the question. So that was, actually I should maybe stop there because that was the story of classical probability theory and Shannon theory. And I'm going to kind of change topics in a moment. Okay. So let's now define a category that generalizes finite probability spaces to the non-commutative setting. So here we're going to work with objects that are pairs where A is an algebra and omega is a functional on that algebra. And you don't really need to know all of these definitions because I'll give examples that show you how this reproduces finite probability spaces in a moment. But take that these are the data for this category. And a morphism between any two such objects is a star homomorphism that preserves the states. And preservation of the states here means that I have a functional on A here. I have a morphism F from B into A, and I have a functional on A, and the pullback, after I just compose these two maps, has to agree with that state. And again, I'll show you examples in a moment. In fact, right now. So if we look at our previous example of finite probability spaces, such a probability preserving function defines a homomorphism on the algebra of functions on those sets. So here, CX denotes, that's a typo, it should be math BBC, is the C-star algebra of functions. So just think an algebra of functions, you can take complex conjugates, you can add functions, you can multiply functions, and you can also compute the norm of functions. So I have this algebra of functions, and what I do is the associated star homomorphism takes a complex valued function on X. Sorry, I'm describing the state now. If I have a state omega on C of X, what it does is it takes a complex valued function on X, and it's supposed to spit out a number. So if I apply this omega to the element in my algebra, which here is a function, then there are actually the probability measure. I can evaluate this function at the point X, multiply it by the value of that probability, and then sum over all of those elements in X. This is exactly the expectation of the function with respect to the probability measure P. So all I'm doing is I'm taking the average of this function with my probability P, and that's what's defining my state omega. And a similar story happens for functions on Y. Now let me talk about the last ingredient in here, which is this map F. F is just related to the original function between the probability spaces by pullback. So if I have, again, a function on Y into the set of complex numbers, which is, again, an element in this algebra, and I can pull that function back onto X, and that gives me now a function on X. So that's exactly what I mean by this function. And in this way, we see that the category of finite probability spaces sits inside of the category of these not necessarily commutative probability spaces, where we talk about algebras, by just taking the algebra of functions on those sets and viewing probability measures as functionals on those algebras. So
it sits inside, but it's commutative. The full embedding is commutative C-star algebras.
Exactly. This is just that special, exactly. And that's maybe a very good point to emphasize, that this is only a small part of this category, right? It's only looking at the commutative structure, and then there's this whole other part of this category that finite probability spaces don't see.
Right. But not every commutative C-star algebra comes from this way either. So it's smaller than, it's like finite dimensional C-star algebras or something.
Yeah, I'm always doing things finite dimensional just because infinite dimensional things get quite technical very fast.
Okay. Good.
So my apologies in advance to anybody who's hoping anything infinite dimensional would appear here today.
No, we don't like that. We don't like infinite dimensional. Go.
Great. Right. So now let's look at another kind of example. So let's go back to now linear algebra, and let's look at m by m matrices. So this is just my notation for m by m complex valued matrices. And a matrix is self-adjoint if you take its complex conjugate and it equals itself. So that's what I'm calling an observable. And every observable, if we
mean complex conjugate transpose?
Sorry?
Did you mean conjugate or conjugate transpose?
Conjugate transpose.
Okay.
Thanks. And if I take the set of its eigenvalues, I'm going to call that set, that finite set, sigma of A. So I think that's the usual notation, but and because again we're working in finite dimensions, this really is a set of eigenvalues. and they're necessarily real numbers because A is self-adjoint. Now let's take an arbitrary state on this matrix algebra. And again, we're just going to think of this as an expectation value, but now we're thinking about this on a non-commutative algebra. So we're thinking of this as some generalized expectation value for, non-commutative algebras here. And we're going to take a very particular function, a very particular star homomorphism from the algebra of functions on this spectrum into our matrix algebra. So we're going to take our functions on the spectrum and get a matrix out of it. This is essentially the functional calculus, but in a very friendly way that you can explain to undergraduates. So it's going to take the specific function. So let's take an eigenvalue lambda, and I'm going to call E lambda the function whose value is 1 at lambda and 0 everywhere else. So you can think of this as like a unit vector. You can think of this this algebra, the functions on the spectrum, as having a natural basis, and that natural basis comes from these functions that take value 1 at every one of these points and 0 elsewhere.
Arthur, excuse me. Can you just say again what is required of a state?
Oh, yeah, the technical, it's a positive unital functional. So that means if I take any self-adjoint matrix here, which has non-negative eigenvalues, then the associated complex number has to necessarily be non-negative. That's one condition. Second condition is that if I take the unit matrix, the identity matrix, then it has to give me the number 1. And then the last condition is the fact that this has to be a linear map.
Okay, thank you.
Mm-hmm.
Can I be heard? Yeah. I just want to say the state is you can think of it as a trace, right? The trace. If we think of matrices, then this is just a trace.
You're correct. You're correct, and I'll mention that. I'll mention that I think on the next slide, actually.
Sure.
But for the purposes of this example, you don't even have to think in those ways. Just think of this as some way of computing expectation values of something physical.
Sure.
What I call an observable. But you're right. Okay, great. So let's describe what this star homomorphism F does. It takes this eigenvalue and this function that gives you 1 on that eigenvalue and 0 everywhere else. It goes to some, first of all, it goes to some projection, and it specifically goes to the projection onto the eigenspace of that eigenvalue. And then what you can do is you can take these two maps together. We have this state on we have this expectation value, this family of expectation values on our matrix algebra. We have this function here. And when I look at the two together, I end up getting a function from the algebra functions to the complex numbers. And that's exactly a state on the commutative algebra now. So we get a probability measure on the set of eigenvalues from such data. And the interpretation of this probability measure is that if you give me any specific eigenvalue, then the probability that that eigenvalue will be observed, like if you're doing this experiment in a lab and you have a specific observable A and you have a physical setup, then the observed eigenvalues that you will get have probabilities weighted exactly by this probability measure. And now let me come into that theorem that was mentioned just a moment ago that gives a convenient way to write states on matrix algebras.
Can I ask a question?
Yes.
Before you move on? So usually in quantum mechanics, I imagine measurement to give me something real. Would that be like norm square of this, the image of the thing you wrote?
Back here? Oh.
Oh, sorry. Oh, that would be the, yeah.
I see. So you will Yeah, so I think the answer to this question is the fact that this does end up being a state. So it is positive and unital. I'm not sure if that.
Does that mean it's like real number? Or?
It will, if you give me a self-adjoint element, it will give you a real number.
Okay.
And that describes the expectation value of measuring that observable.
Okay.
So for the example, if it was something like 1 over the size of the matrix times the trace, it would be counting the relative multiplicity of the eigenvalue. Counting the number of times the eigenvalue occurs relative to the total number.
Yeah, that sounds right. I think that sounds right. So now let's get to this result that explains how states are related to what are called density matrices. So if you give me any state, so again, a positive, unital, linear, functional on a matrix algebra, then there exists a self-adjoint, non-negative matrix whose trace is 1 and such that the functional is equal to the trace and then multiplied by by that density matrix. So my notation here means if you see this dot here, that means I'm plugging in an arbitrary matrix A to compute the associated number omega of A. And conversely, given any such operator, the functional trace with respect to that row is a state. And this is what's normally called a density matrix. And I think normally the way that this is introduced in a quantum mechanics course is that this is usually defined first through a very different approach. But I think this one's a very natural one because viewing it as a functional, you can interpret it as families of expectation values no matter which observable you give me. So let's look at an example. And I'm going to call this the Epr morphism in non-commutative finite probability spaces. If I take 4x4 matrices, which I'm going to think of as 2x2 tensor 2x2, and I'm going to associate the specific state associated to the rank 1 density matrix. So this means that you can check that this matrix is actually a projection, and rank 1 just means that it's a projection onto a one-dimensional space. Doesn't matter what these numbers are, by the way. I'm just writing it so you have it for reference, but the specific numbers don't matter for what I'm saying. In fact, there are many density matrices that will give the same result as what I'm about to say. And let's also set another density matrix, this time on 2x2 matrices, to be just 1/2 the identity. So Scott was saying earlier, this is 1 over the dimension times the trace is the associated state. Now there's an inclusion map from 2x2 matrices to 4x4 matrices. In fact, there are many, but you can take any of them actually. So just take whichever one you want. And one of them is to send a matrix, send a matrix A to A00A, for example. And it turns out that with the states defined here, this map is a state preserving star homomorphism. And this example is very special because it illustrates a potentially counterintuitive fact, which is that a deterministic process can take a pure state, which is this density matrix on the initial algebra, and it pulls back that state to a new state, which is completely mixed. It's no longer a rank 1 projection. It has eigenvalue 1/2, 1/2. With multiplicity 2. And if you try to compare this to the finite probability case, this cannot happen. And the reason this cannot happen is, again, any function always can, at the worst case scenario is either an element goes to another element or 2 elements combine to 1. So you can always, but you can never start with a pure state, which is, imagine you just have a single water droplet with volume and everything else has no volume. You can't rip that water droplet apart in a deterministic way to construct a split water droplet. But this happens in the quantum mechanical setting. And you might notice that the directionality here is a little bit different. I'm now referring to the codomain as the initial state and the domain as the final state. And this just has to do with the fact that the algebra of computing the algebra of functions is co-functorial. So there's a little bit of a reversal here between going from probability spaces to algebras, where I just have to remember that what I think of as what was initial before is now the codomain. So I call this Epr morphism because it's named after Einstein, Podolsky, and Rosen, who analyzed a very closely related example in a different setting and illustrated some of the very strange features that these kinds of states and maps satisfy. Though technically the example I presented here is due to Bohm. And in fact, we'll see some of these strange properties later, although I've already given a hint at one of them. So associated to a morphism in this category, we can compute, associated to any object or in this category, we can compute the von Neumann entropy. And let's start first a little bit simple with working with a specific matrix algebra. So the von Neumann entropy here is, we're going to use the functional calculus to define it. But again, we've already talked a little bit about it. And what you do is you diagonalize your density matrix by finding some unitary. And then once you've diagonalized it, all you have to do is compute the Shannon entropy associated to that. So that's what this formula here means. If you don't know what it means to take the logarithm of a matrix, you would make sense of it by trying to diagonalize and then using the result for numbers and probability measures that I expressed earlier. But if you have a more general state, we need to understand states on more general C-star algebras. And an arbitrary C-star algebra looks like a direct sum of matrix algebras. So you can think of this as like a vector of matrices. And then the way we multiply vectors of matrices is we multiply component-wise. And if you give me a state on a direct sum, then there exists a unique probability measure on X, which is on the space, I'm going to call X the index set for that direct sum. So X quantifies how many components there are in these vectors. I think it's very standard to write this as the direct sum from I equals 1 to n, but I don't want to necessarily impose that there's some order structure here. So I've just indexed my sets. I've just used an index set without an order. And so nevertheless, I can associate a probability measure on X. And I also obtain a family of density matrices on the specific matrix algebra components. And I'm not writing out the details of how you do this, but you can try to do this actually diagrammatically too. But the result is that there exists a family of probability measures and a family of density matrices such that if I compute the state on any vector of matrices, then all I do is I compute the expectation with respect to the density matrices, and then I weight each of those by the corresponding probabilities. So I think of this as combining both the classical and the quantum features at the same time. And you can define the von Neumann entropy of such a state, and essentially it combines both the Shannon and the von Neumann entropies. So you could take this as a definition, and we'll do that. It's the entropy of the probability measure plus all of the entropies of the density matrices weighted by the corresponding probability measure. The specific formula won't matter if it looks a little bit foreign to you. But I will mention one thing, which may sound a little bit, if you actually try to construct the associated density matrices, they might not be unique. And the only reason that they might not be unique is if these probabilities px's happen to vanish. If they happen to vanish, however, then that doesn't affect this expression at all. And no matter which representation you choose, which density matrices you choose, you'll always get the same entropy. And in fact, the density matrices will even be equal if the probabilities are non-zero. So let's go back to our earlier example just to make sure that this is consistent. So again, we have a map of probability spaces and the associated pullback star homomorphism on the algebra of functions. And we can compute the von Neumann entropy difference, and we obtain exactly the difference of entropies on the associated probability spaces. And so this entropy difference agrees with our earlier definition on finite probability spaces. And just as in the case of finite probability spaces, the von Neumann entropy difference defines a functor. Again, for very obvious reasons, because I'm taking the difference of two things, and when I compose, then I'm just taking the sum of those differences, and the middle term always cancels. But many natural questions arise. First of all, does this necessarily factor through the non-negative numbers? Is the difference always non-negative? And it turns out that it might not be non-negative. And the earlier example that we gave before actually illustrates that that can happen. So in this case, we started off with what's called a pure state because it corresponds to a rank 1 projection. And if I computed its von Neumann entropy, then the only eigenvalues are 1 and 0, and then the entropy of that is 0. But when we pull it back, we get a fully mixed state. The eigenvalues here are 1/2, 1/2, and so when I compute those entropies, I get minus log 2. And so the difference is actually negative in this case. Therefore, this entropy difference cannot factor through the non-negative real numbers. And I should mention one of the important things here is that although I'm not going through the proof of the original Baez and Fritz and Leinster theorem, this fact is used to prove when you try to construct the entropy difference. This fact is used to prove that isomorphisms have 0 entropy difference. So by dropping this assumption, it's no longer clear if I start off with an arbitrary functor satisfying some nice properties, but I don't assume that it lands in non-negative real numbers, it's not clear if it's even possible to prove that the difference associated to an isomorphism is 0. So that's the first indication that this is potentially going to be a difficult thing to characterize. So there's another structure that we looked at in the finite probability case that we need to extrapolate to the non-commutative setting, and that's that of a convex structure. And you could try to do this pretty simply, just as we did before, just by using the direct sum of algebras. If I have 2 probability spaces, and I have some number between 0 and 1 lambda, I can take the direct sum of algebras, and then I can take the sum of the associated states. And the meaning of this is just if you give me an arbitrary element in A plus B, so an element of the form A plus B, then what I do is I just evaluate A on omega, C on B, and then I take the convex sum of the 2 results. And the convex sum of morphisms is just the direct sum. And this agrees with the convex sum we defined earlier on finite probability spaces if you, for instance, take these algebras to be commutative. And without so much work, you can prove that the difference of von Neumann entropies defines an affine functor just like it did in the classical setting. But it's not classified by these assumptions, even if we required it to factor through the subcategory of commutative C-star algebras. And an example is an example of such a functor is the following. So you can try to do something very naive, which is if you give me any two states on direct sum algebras. So A, for instance, here is the direct sum, the same one we had earlier, a direct sum of matrix algebras indexed by some set X. And I can just ignore the density matrices completely and then just compute the Shannon entropy associated to these probability measures. That's still a well-defined assignment, and it satisfies the property that it's affine and it's functorial, and it factors through the non-negative real numbers. But it's not the von Neumann entropy. So we need to modify this structure somehow. And the problem with the previous counterexample is that it doesn't see the internal convex structure of matrix algebras. So this is a very poor person's picture of me trying to draw what I think, and it's a very poor attempt. But on the left, you see a probability simplex associated to a set with 3 elements. And on the right, it's a probability thing associated to the direct sum of 3 matrix algebras. And what I've depicted here is that a point, which corresponds to one of these matrix algebras, has this additional internal structure that is missed by the convex sum that we defined earlier. And it suggests that our definition of convex structure is insufficient. And so we need to include the possibility of taking convex combinations of density matrices as well. And one way to solve this problem is to actually work with what are called fibrations. And I'm not going to define these completely, but I'll give you the data associated to them. And a fibration is essentially a functor from one category to another, satisfying a certain lifting property. And rather than saying what that lifting property is, I'll give examples which I think are much more intuitive. So first, I just want to set up the fact that associated to every object in the base category, so X is going to be my base category, I can construct a category over that object, which I'm going to think of as the fiber. And it consists of objects in the total category E. So I'm using the language of bundles here, but I hope it also applies, it helps keep these ideas together. And the objects are going to be objects such that when you project down into X, they hit the little element X. And if I take any morphism, then it projects down to the identity morphism. And the category EX is called the fiber, and the morphisms are called vertical morphisms in analogy to the case of what happens in the case of bundles. A fibration is called a discrete fibration when these categories are discrete categories, which means they have no non-trivial morphisms. So our first example, I think, is just going to help a lot. If we take an arbitrary algebra A, then we can look at, so this is our base category is the category of all finite dimensional C-star algebras. And here we have non-commutative finite probability spaces. And we know that those are pairs of a C-star algebra and a state on that C-star algebra. So essentially what we're doing in this map is we're just forgetting the information of the state. And this turns out to be discrete fibration because the set of states over an algebra is that it's a set of states. And if I have a star homomorphism of algebras, then I get I think I drew this in the wrong direction, but yeah, I did draw this in the wrong direction. I get a pullback map from states on A. Oh, sorry, this direction is correct, my bad. This direction is correct. But I think of this map as pulling back the state on A onto the state on B. And right, so the fiber over every object is the set of all those states on A. There's another fibration. This time it's no longer discrete. In fact, it's like the opposite, where over the category 1, which is just a single object category with just the identity morphism, there's this category of all real numbers. That's also a fibration. But again, here it only has one object, and the only non-trivial thing in this category are the collection of morphisms. And so how do you make sense of taking convex combinations of stuff in the fibers? You can formally define this by taking the pullback. So if you have two fibers, you look at their pullback, and when they agree, when the two fibers over the two objects agree, then you can make sense of taking convex combinations in that common fiber. So you just define this pullback. And what is this as a category? It's objects or pairs where the image into the base, where the images in the base agree. And if I have two morphisms, then the images of those morphisms also have to agree. So that's how I'm defining this category of this pullback here. Or I mean, you could take it to be the pullback by the universal property if you like that more. And then the composition is just induced from the composition in the ordinary Cartesian product. And let's take our example of finite probability spaces, and the base is this category of C-star algebras. Then what we can do with this pullback is we can take convex combinations. So to every object in the pullback, which is a pair of objects, but because it's in the pullback, the algebra A, when I map down with this map pi, they have to agree. So what this says is I have two states, possibly different, but on the same algebra. Then the assignment that this functor gives is a new state on that same algebra. And that new state is going to be the convex combination of those two states inside that algebra. And if we have a morphism, so you can check by applying the pullback construction to these categories, that a morphism is just going to be, it's supposed to be a pair of morphisms that agree in the base, but they both necessarily have to be the same morphism in this case. And what we do is we just apply that morphism again. So nothing really dramatic happens on morphisms. What really happens in this construction is the convex combination of states. But the fact that this is state preserving is not necessarily trivial, but it just follows from the fact that F is state preserving for both of these, for these two states, omega 1 and omega 2. So because it's state preserving for each of them, it's state preserving for any convex combination of them as well. And similarly, we can view real numbers as a convex fibration too by taking convex combinations of real numbers. And notice that this new convex structure on non-commutative finite probability spaces is different from the previous one we introduced, which didn't take into account this additional internal structure on each of the algebras A. But because it's different, you can ask how the two are related. In other words, can we see the previous convex structure as a special case of this new one? And the answer is yes. If it wasn't yes, I'd have to stop. But let me just go through this and show the picture, because I think the picture is going to explain this more than the words will. If I take two disjoint sets, for instance, and I take their convex combination, then that would be the old convex structure where we just concatenate two spaces and concatenate these two probabilities with the associated weights. But we can also take a space with two probability measures on it that are just supported on different subspaces. And there's a formal way, and there's a way to make all of that rigorous by introducing the notion of mutually orthogonal states. And if you've taken a class in measure theory or probability theory, you might be familiar with mutual singularity, I think it might also be called, of two probability measures or two measures. These are just measures that are supported on disjoint sets, essentially disjoint sets. And the convex combinations that I introduced earlier, when you focus your attention on such pairs of states, then that's what reproduces the external convex structure that Baez, Fritz, and Leinster introduced in their classification. But we also have to talk about morphisms too. And how do you associate the convex sum of morphisms? And for that, you make sense of what it means for two probability, there you think of it as two probability preserving maps that preserve the measures onto orthogonal or disjoint subsets as well. So you can make sense of that in this state setting as well by saying, if I started off with mutually orthogonal states, applied a process, a single process, F, and then the resulting states remain orthogonal, then we say that that morphism preserves this mutual orthogonality. And that's what this picture is showing here, where I've taken the blue probability measure and the red probability measure on the initial space. I applied a function f that didn't mix these probability measures around. It took the blue ones to the blue ones and the red ones to the red ones. That's an example of a morphism that preserves the mutual orthogonality of these two states. And so just by looking at this picture, you can immediately see that this should reproduce the Baez, Fritz, and Leinster situation of taking orthogonal or of taking convex sums. And it does, though the details are surprisingly annoying to write down, but you can make rigorous sense of the equivalence between these two perspectives. And when you do this, the von Neumann entropy difference functor satisfies this affine condition, provided that the states are mutually orthogonal to begin with, and after you apply the star homomorphism F, they remain mutually orthogonal. So it's a kind of a generalization of the affinity condition from Baez, Fritz, and Leinster that incorporates the fact that we can add these states inside of a fixed algebra as well. And the affine condition only holds when this orthogonality is preserved. And when this happens, we say H is orthogonally affine. So with these ingredients, modulo what continuity means, it's a little bit more subtle here, but it's not bad either. But ignoring the continuity condition, if you give me any continuous and orthogonally affine functor of fibrations, for which, and this is one of the assumptions, so here are the assumptions that we make besides that one. If I take the map, there's always a canonical map from the complex numbers to any unital algebra that takes the unit here to the unit in your algebra. This is like the map on finite probability spaces that takes a probability measure and forgets all of that information by identifying all of the points to a single point. So if we assume that this functor is always non-negative for those kinds of maps, in other words, it's just quantifying that there's some kind of information associated to such a map that's not negative, which is a very weak condition. For all states, and then with equality on pure states, for all C-star algebras, then this functor is characterized by these axioms as the von Neumann entropy difference between associated to the state preserving star homomorphism. And Let's see, I can't remember if yeah, great. Any questions so far? I'm almost done, yeah.
Arthur, so when you were talking, I was thinking that when you're looking at finite probability spaces and you have this affine structure, you have the way of taking affine combinations, you can generate the whole category of finite probability spaces by starting with just one point.
Yes.
But if you go to the matrix algebras, that doesn't work because you kind of need one for every dimension.
Exactly.
So my question is, sorry if I asked it a slide or two too soon, but
no.
Is it true that the whole category of non-commutative finite probability spaces are generated by like a one-dimensional matrix algebra and then your new kind of affine structure or something like that?
No, it's
you
not.
Need one in every dimension?
Yeah, if I were to try to say that there's like a class of objects that generates all probability measures, yeah, I would have to include all dimensional matrix algebras in that class, and that's too much, in my opinion. So instead, what this does is it bypasses that by just saying, how should we take convex combinations between different objects and within the objects? But you're absolutely right. If the finite probability spaces is completely convex generated by a single object, and this exactly fails for the non-commutative setting, I would need an infinite number of objects to generate it.
I see.
Yeah, it's a very good point. So what's the difference between these axioms and the ones from Baez and Fritz and Leinster? Because if you look at them, they look very different. Other than the first ones, continuity, orthogonal infinity. I kind of explained how orthogonal affinity is very closely related to their convex combination, their affine condition, but we've now included the taking convex combinations of probability of states within a specific algebra. And the other condition that they had was that this was you landed in non-negative numbers. I've actually replaced it with a much, much weaker condition, which is that not all morphisms land in non-negative numbers, just very special ones and kind of very obvious ones that you would want to be non-negative, which is just sort of giving you the information content of any probability space. So we just say that each probability space has to have some information content. So that's one assumption, which sounds very, very weak. And then the other assumption, which may not be totally obvious, is that this information content vanishes when we have a pure state. So a rank 1 projection, a probability measure that's localized on a single point. And I'll explain a little bit about the relationship between this assumption and Baez and Fritz and Leinster's. But I might as well say it now. It's that it turns out that these assumptions are equivalent to their assumptions on the category of finite probability spaces. So by assuming this orthogonal infinity continuity, by assuming this condition here, and then equality on all pure states, one can show that when you apply this functor to any morphism in that subcategory of commutative algebras, it will necessarily be non-negative. And this is actually a very special feature of commutative algebras because they satisfy a very special property, which is that any morphism of probability spaces has a stochastic section. And by section, I mean a map that goes back in the opposite direction, that takes the probability. Remember this water droplet picture, it takes these probabilities and splits them up, reproduces the probability measures back by dividing these water droplets up appropriately in such a way so that when you project back down, you get back what you started with That's what I mean by a stochastic section. And it's because of this fact, the fact that these things exist in the category of finite probability spaces, allows you to prove that this functor always factors through non-negative numbers on that subcategory.
So excuse me, can I ask a question? This stochastic section, is it like a conditional probability basically?
Yes, it is. So
Right.
there are many names for this thing. They're called regular conditional probabilities, disintegrations, optimal hypotheses.
Okay.
They go under many different names.
Mm-hmm.
Exactly. It's a conditional probability. And in general, for non-commutative probability spaces, if such a stochastic section exists, or the analog of a stochastic section, you can prove that the entropy difference is also non-negative whenever that happens, even for non-commutative spaces. But for non-commutative spaces in general, such things do not exist. And that's why I think these axioms are a little bit more natural from that perspective. And they can be used to classify or to characterize this entropy difference functor. And actually, what I just said is roughly what's exactly on this slide. So I might as well skip that. So thank you very much. If you have any questions, please let me know.
Okay, let's thank our speaker.
Thank you.
Anyways, questions, fire away.
Hi, I have a question.
Mm-hmm.
So you mentioned at some point that in the quantum case, this positivity fails, right? When you can have this process that decreases entropy. So I want to ask you first, how should I think of that physically? And second, if your result at the end tells me any sort of bound for how much it can vanish, starting from a given state.
So let me answer the first question first. So, right, so the question is essentially, what is the meaning of the fact that it could be negative, essentially, right?
Yeah.
So, so I'm not an expert on this, but I will say what I have read, which is that what you can do is, usually if you think of this in the finite probability case, you're thinking of this as information being lost. So if you've ever heard of Landauer's principle, which says, if you do a computation and you lose some kind of information, then the net entropy of the universe increases. What this is saying is sort of like the opposite. It's saying you perform a specific task, and then you have the ability to perform an additional, let's say, a quantum protocol for free without using any extra energy, for instance. So it allows you to do certain quantum protocols because you've somehow gained some information. You've gained some processing power to do a specific task. And your second, does that kind of answer the first question?
Kind of. So it sounds like something like you're borrowing entropy from some kind of entanglement entropy.
You can think of, yeah, exactly. You can think of it. And then you're using it for, you can store it and then use that later at a later point.
I see. So if I add to the picture entanglement entropy, would I then restore this positivity? Or I'm a little confused about where, this thing called entanglement entropy.
This thing is entangled. This is the state, the EPR state is the fully entangled state. And then what you're doing is you have these two observables, Alice and Bob. Mm-hmm. And you could say Alice, the associated state for Alice is this totally mixed state. Mm-hmm. And Alice, I think the idea is like Alice can use this entanglement at a later point in time to transfer information to Bob. Something like this. It's called a state merging protocol, though I don't quite remember the details exactly. I have to admit I forgot your second question.
My second question is, if I start with a given state, you might imagine that if you might want to bound for how much that entropy can decrease, can be negative.
Yes.
Out of starting from it. So does your theorem give you any sort of bound like this?
Well, I mean, you mean like before know it's the entropy difference. I haven't thought about trying to compute it abstractly, like from the.
No, I mean, like, for example, if you start with just a classical state, right? I imagine whenever you map this out to something else, your entropy difference is going to be positive.
Yeah.
Right. Yeah. So you know, I measure how quantum it is by how much.
How negative it is.
By how negative a map going out of it could give the entropy difference.
I don't know the answer to that, but I would definitely think it's bounded, and it's not bounded by what maps into it. Like it's bounded by the specific algebra with that state. Yeah. I think it's bounded. I wouldn't be surprised if its upper and lower bounds are at the worst, you know, n log n or something, or whatever the maximal entropy could be. But maybe you could do something better. I'm not sure.
Thank you.
Any other questions?
Can I ask one?
Please.
Well, thanks for the talk. So do you have some ideas about how to work in the non-finite dimensional setting? I mean, what are some ideas in terms of an appropriate setup and how you would extend this, and what are some difficulties?
Right. So one of the most immediate difficulties in the infinite dimensional setup is that even in the classical setting, in the infinite dimensional setup, entropy could blow up. Like it could be negative infinity, for instance. Like if you have a Dirac delta measure, like if you have a Dirac delta measure on some even reasonably nice measurable space, and the associated entropy with that is minus infinity. I don't know if there's a way to bypass this by using like densities or something, or ratios, but what you can do is you can take a different approach by computing relative entropies. And it would be a slightly different setup than this. And people have had more success finding functorial characterizations of relative entropies in the infinite dimensional setting than they have with just ordinary entropy. And I'm pretty confident that one can characterize these, at least in a reasonably nice von Neumann algebra setting for the relative entropy. Though I've thought about it a little bit, but I don't see this fibration picture from that perspective. But what I do see more of is this idea of having these stochastic sections that I mentioned earlier, which here in this talk, I only used the properties about these stochastic sections on finite probability spaces. But in that setting, one would actually use the existence of and their characterization in the non-commutative setting. But I think it has a more chance of getting a functorial characterization for the relative entropy.
Thank you.
Okay. Arthur, more, John, ask.
Well, I was just thinking about what Scott's question. So I once heard Gromov say that really infinite probability theory on infinite sets is really a bad idea anyway. And that you should really be studying something like pre-sheaves on the category of finite probability spaces. I don't really remember what the detail was, but do you know what that is? And does that help you sidestep the infinite dimensional case in any way? That somehow the theory on the finite probability spaces was really all you really need. Mm-hmm. And then some structures on those or something.
I don't know. I don't know the answer to that. But I can see a lot of the issues with the infinite dimensional setting, like which category you pick, and whichever one you pick, it always has its drawbacks, whether you're working with standard probability spaces, Borel spaces, Polish spaces, arbitrary measurable spaces. Each one has its pros and cons, and it gets, it gets a little bit hairy. Which one is the best one to use? But I haven't thought about this pre-sheaf perspective.
Yeah. So can I ask one other different question? So there's these other kinds of entropy, like Renyi entropy, or do you have some sense in which if you weaken your axioms that you pick up these other kinds of entropies somehow?
That's a good question. I haven't thought about it at all, but based on my understanding of Baez and Fritz and Leinster's characterization, they modified the affine condition by having an appropriate power, for instance.
Oh, right.
And I think to construct the Salas entropies, I believe that's what it was. And I would not be surprised if you can do something very similar here, though I haven't thought about it. Because essentially I do keep this convex structure in the affine condition just as it was before. So it might be possible.
I see. Okay, thanks.
Anyways, let's, if there's no other questions, let's thank Arthur again. Thank you, Arthur.
Thank you.
This is the end of the fall 2020 season. We finished it off with a bang. I just want to say, in the spring, we're going to have Tobias Fritz is going to speak, and Ross Street, and Peter Hines, and Rick Blut, and a few other people are lined up already. So it's going to be nice. And I think Tobias will be speaking about this probability theory stuff again. Anyways, thank you all. I wish you all a happy holidays and safe, and be, well, in France, they're not worried about snow, but we're worried about snow here. And I wish you all the best. Have a wonderful New Year's and a wonderful Christmas and everything. Okay?
Thank you.
Okay. Take care.
Thank you, Arthur. Great talk.
Thanks.
Thanks, Arthur.
Take care.
Thanks. Bye.